Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today, we begin our deep dive into the fascinating world of nuclei, Unit 13. We promise to give you a simple, exam-safe explanation that, removes all that fear from nuclear physics.
Right, because this is a unit where the rules seem to change completely. We leave the familiar world of mechanics and electricity, and it can feel very abstract.
Absolutely. So let's start not with a formula, but with a simple, everyday question. You know that atoms make up everything, but have you ever stopped to think, why does a common smoke detector start beeping when there's smoke?
Hmm. I would guess it has something to do with maybe a light sensor or perhaps a heat sensor, something simple related to electricity. I definitely wouldn't think of atomic structure.
And that's where it gets really surprising. Actually, many smoke detectors have a tiny amount of a radioactive element called americium-241 inside them.
A radioactive element in a household device.
Yes. This element is constantly releasing invisible particles called alpha particles, and these create a small electric current inside the detector.
Wait, what? An everyday device is relying on radioactivity, a nuclear phenomenon. That seems so counterintuitive.
Exactly. When smoke particles enter, they block these tiny alpha particles, the current drops, and the alarm goes off. To understand this, or even why our sun shines, we first have to understand that tiny, mysterious core of the atom, the nucleus.
Okay, so the physics of a fire alarm is actually nuclear physics. Let's dive into that core then.
So at the very center of every atom, we have the nucleus. It's an incredibly tiny, dense ball made of protons and neutrons, which we collectively call nucleons. But right away, this presents a huge paradox. Protons are all positively charged, and we know from Coulomb's law that, charges repel each other with enormous force.
And they are packed so tightly together. So if the repulsion is that strong, why doesn't the nucleus just explode instantly? Why is matter stable at all?
That is the most important question in this chapter. To get a feel for it, imagine the nucleus is like a tiny, impossibly crowded room.
Okay.
Inside are the protons, people who naturally want to push each other apart. The Coulomb force is screaming at them to separate. But inside this room, there is a mysterious friendship force, the nuclear force. And it's so powerful that these people prefer to stay crammed together rather than leave.
So it's a constant battle inside the nucleus. The electrical force is trying to tear it apart, and this nuclear force is holding it together.
Precisely. The very existence of stable nuclei proves that a new force, the strong nuclear force, must exist at these subatomic scales to overcome that immense Coulomb repulsion. Now, to really grasp the scale, let's build a mental picture. If we could somehow enlarge the nucleus to the size of a tennis ball,
Right.
the whole atom with its electrons would be spread out over 10 kilometers.
10 kilometers. So the atom is almost entirely empty space. That's
Yeah.
really hard to visualize.
It is. The nucleus is about 10,000 times smaller in radius than the atom, but it contains more than 99.9% of the atom's total mass. This density is the key.
Okay, so the concept is clear. How do we define this formally for the exam?
Good question. Now let us see how NSERT defines this structure. Could you read the relevant part?
Yes, it says, in every atom, the positive charge and mass are densely concentrated at the center of the atom, forming its nucleus. The overall dimensions of a nucleus are much smaller than those of an atom. Experiments demonstrated that the radius of a nucleus was smaller than the radius of an atom by a factor of about 10 to the power of 4.
Perfect. So let's break down the components we need. The nucleus is made of nucleons. That's just the collective term for protons and neutrons. We use symbols to identify a specific nuclear species, or nuclide. There's Z, the atomic number, that's the count of protons. Z always defines the element.
Okay, Z is for protons.
Then there's A, the mass number. That's the total count of all nucleons, protons, plus neutrons. And finally, N, the neutron number, is just A minus Z.
You mentioned the nucleus is incredibly dense. Is there a formula to quantify its size and density?
Yes, and this is a very important formula for numerical problems. Experiments show that the nuclear radius R is proportional to the cube root of the mass number A. The formula is R equals R naught times A to the power 1/3. R naught is a constant, about 1.2 into 10 to the power minus 15 meters, or 1.2 femtometers.
So A to the power 1/3. what is the deeper meaning of that? Why the cube root?
Ah, that tells us something profound. The volume of a sphere is proportional to r cubed, isn't it? So
Yes.
if r is proportional to a to the power 1/3, then r cubed must be proportional to a.
Which means the volume of the nucleus is directly proportional to the number of nucleons.
Exactly. And since density is mass divided by volume, and the mass is also proportional to a.
Oh, I see. The A in the numerator and the A in the denominator cancel out, so the density is constant
Yeah.
for all nuclei.
You've got it. The nuclear density is constant, about 2.3 into 10 to the power 17 kilograms per meter cubed. It's millions of times denser than ordinary matter. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Now, this all connects to the next topic. When we precisely measure a nucleus's mass, we find it is always slightly less than the sum of its individual protons and neutrons.
And the mass is less. Where does that missing mass go?
That tiny missing mass called the mass defect is the source of the binding energy that holds the nucleus together. We'll explore that in detail next. But first, let's focus on some silent killers. Common mistakes that can cost you marks. Misconception number 1. All nuclei are radioactive and dangerous. Students often think this because we talk about uranium so much.
So a stable nucleus like carbon-12 is just normal. It's not going to decay on its own.
Absolutely. It's perfectly stable. Remember, stable nuclei are like rocks. They don't change. Radioactivity is the property of specific unstable isotopes, not nuclei in general.
Okay, that's a very important distinction.
Misconception number 2, and this is a big one for calculations. Radius is proportional to the mass number A.
Right. Students might think a nucleus with 8 times more nucleons is 8 times bigger.
Exactly. But the correct formula is R is proportional to a to the power 1/3, the cube root. This means a nucleus with 8 times more mass is only twice as large in radius because the density is constant.
So if I double the number of nucleons, the nucleus gets only slightly larger, not double the size, because it all packs in at the same density.
Perfect. That's the key idea. And finally, misconception 3. The nuclear force has infinite range, like gravity.
But it can't. Right.
Yeah.
Otherwise, we'd feel it all the time.
You're right. The nuclear force is an ultra-short-range force. It only works when nucleons are literally touching at distances less than about 3 femtometers. Beyond that, it drops to 0. That's why we never see it in chemistry or everyday life. Okay, so to help all this shtick, let's use some memory anchors. Here's a catchy phrase for the core paradox. Nuclei are tiny, dense, and full of drama. The drama is that constant battle between Coulomb repulsion and the strong nuclear force.
Tiny, dense, and full of drama. I like that.
For the symbols, remember, Z is the atomic number, which is the proton count. A is for all nucleons, the mass number. And N for neutron number is just A minus Z. And here's a physical gesture. Hold your hands close together, almost touching, and sort of vibrate them rapidly. This is the stable nucleus, nucleons tightly bound.
Yeah.
Then suddenly flick one finger outward. That single moment, that's radioactive decay.
That really gives a feel for it, the suddenness of it.
And for the density, a final extreme association. Remember that 1 cubic centimeter of nuclear matter would weigh 100 million tons.
100 million tons, like crushing Mount Everest into a sugar cube.
Exactly. You'll never forget that density figure. All right, to wrap this up, here are the 3 short exam-safe summary points. 1, the nucleus is the dense, positively charged core of the atom, about 10,000 times smaller in radius than the atom, composed of protons and neutrons. 2, nuclear stability is governed by the strong nuclear force, which overcomes the massive Coulomb repulsion at very short ranges, around 1 to 3 femtometers. And 3, nuclear properties are defined by Z and A, and the radius scales as R is proportional to A to the power 1/3, which gives a constant extreme density across all nuclei. To get maximum marks in 12th CBSE physics, chemistry, and maths, visit ProfSam.com.
That is ProfSam, right?
Yes, ProfSam.com. Thank you for joining us for this deep dive into the introduction to nuclei. We hope you feel more confident about this foundational topic. Keep studying hard, and we will see you next time.